Good day, everyone. Today we are going to solve two real-life problems involving the basic concepts of limits and continuity of functions.
Our first real-life problem is about a group of young researchers conducting an investigatory project about finding the number of bacteria colonies present in their junior high school buildings' water fountains. In a previous study, it was found out that a certain colony has a growth rate of 20% each hour. The group had collected from 3 water samples from the fountains located in the first floor, second floor, and third floor, which are respectively referred to as Sample 1, Sample 2, and Sample 3. These samples were then placed in a Petri dish containing agar. And after 12 hours into incubation period, it was found out that there are at least 2 colonies present in the first sample, 3 colonies in the second, and 5 colonies present in the third. With that, the group would like to determine the colony count growth formed in all 3 samples after the 24-hour incubation period or after 12 hours prior to the first recording of the colony count growth. Second is to determine the most contaminated sample after the 24-hour incubation period. In this problem, we will be dealing with an exponential function where we will be using the formula y is equal to a multiplied to the quantity of 1 plus r raised to the power of x, where y represents the colony growth, a represents the starting number, r represents the growth factor, and the duration of time represented by the variable x. Let us now determine the colony count growth present in sample 1, wherein we already know that a is equal to 2, which is our starting number, r is equal to 0.20, which represents the 20% growth rate, and a 12-hour duration represented by the variable x. Substituting these values in the formula would then give us the equation, the limit of 2 multiplied to the quantity of 1 plus 0.20 raised to the power of x as x approaches to 12. As you can see on the screen, here we have the table of values, and we will be using this table of values to determine the limit of this function. Coming from the left side, we need to identify x values that are slightly less than 12. So if we start off with, let's say, 11.9, we can get closer to 12 by looking at 11.99. Then we could put a string of 11.999. And now coming from the right side, we are going to choose x values that are slightly bigger than 12. So we start off with a value of 12.1, then something slightly smaller would be 12.01, then we have 12.001. And then what we have to do now is we are going to get their corresponding y values. So if we go over the calculator, we are going to type in our function, which is 2 multiplied to the quantity of 1 plus 0.20 raised to the power of x. Here we simply have to substitute the x with our values on the table. So for example, 11.9 would result in a corresponding y value of 17.51002732. Rounded off to 3 decimal places would result to the answer shown on the screen, which is 17.510. We do the same thing for 11.99, giving us 17.800, and 11.999, giving us 17.829. So we simply do the same thing with the x values coming from the right side, like 12.1 giving us 18.160, 12.01 giving us 17.865, and the corresponding value of 12.001 is 17.835. So now that we have this table of values, we need to start paying attention in the center, wherein as we get closer to 12, coming from the left side, our y values are increasing towards the value 17.829, or 18 when rounded off. The same thing is happening as we approach from the right. We can see that y values are decreasing towards 17.835, or 18 when rounded off. So what this tells us, since our left and right limits are equal, our limit as x approaches to 12 of the function is equal to 18. In solving for sample 2, we simply follow the process we used in solving for sample 1. But this time, we have to replace the variable a in our formula for colony growth to 3, which is our starting number. So for sample 2, we are going to find the limit as x approaches to 12 of the function 3 multiplied to the quantity of 1 plus 0.20 raised to the power of x. We will once again plot the same x values and simply substitute it to our function. Take 11.9 for example. The function will now be 3 multiplied to the quantity of 1 plus 0.20 raised to the power of 11.9, which results to a corresponding value of 26.26504,098, or 26.265 when rounded off to 3 decimal places. Simply substitute the other x values as well until you get all their corresponding y values. Once your table of values is complete, it should look similar to what is being flashed on the screen right now. Observe once more how as we get closer to 12, coming from the left side, our y values increases towards the value 26.743 or 27 when rounded off. The same thing is happening as we approach from the right. We can see that y values are decreasing towards 26.753 or 27 when rounded off. Since our left and right limits are equal, our limit as x approaches 12 of this function is equal to 27. Solving for our last sample, we simply have to change our a or starting value to 5 once more. Therefore, we are going to find the limit as x approaches to 12 of the function 5 multiplied to the quantity of 1 plus 0.20 raised to the power of x. Using your table of values, simply substitute the same x values we used for the past two samples into the new function to get their corresponding y values. Once you have completed your table, your value should be similar to what is being flashed on the screen right now. Notice as we get closer to 12 coming from the left side, our y values are increasing towards 44.572 or 45 when rounded off. The same thing is happening as we approach from the right. We can see that y values are decreasing towards 44.589 or 45 when rounded off. Since our left and right limits are equal, our limit as x approaches 12 of this function is equal to 45. At this point, we can now determine the colony count growth formed in all three samples after the 24-hour incubation period or after 12 hours since the first recording. The number of colonies present in sample 1 after 12 hours will be 18, 27 in sample 2, and 45 in sample 3. Therefore, the most contaminated sample after the 24-hour incubation period would be sample 3, with a total colony count of 45. If placed in a graph, here's how the colony growth formed in all three samples after the 24-hour incubation period or after the first recording would look like. Here, you can see and confirm that the limit as x approaches to 12 is indeed equal to 18 for sample 1, 27 for sample 2, and 45 for sample 3.
Problem number 2. Dr. Yoon is going to perform a surgery that's going to last for 5 hours. How much dosage of anesthesia does he need to inject to his patient to make her stay asleep for the whole 5-hour surgery if the formula of the anesthesia is 8x plus 1 over x squared plus 1? So we are going to find the limit as x approaches to 5 of the function 8x plus 1 over x squared plus 1. So we are going to be using the table of values. As what you can see, there is an x, which is already encoded, and we are going to use that to find the f of x. For example, 4.9. We are going to substitute that to the limit of our function, which is now 8 times 4.9 plus 1 over 4.9 squared plus 1. We are going to get the answer of 1.607, and that is the f of x. So after substituting all of them, you're going to know that the limit as x approaches 5 from the left is equals to 1.577, and the limit as x approaches 5 from the right is also 1.577. Now the next thing we are going to do is also substitute 5 to the limit of our function, which will give us 41 over 26, or in decimal 1.577. Therefore, the limit as x approaches 5 of the function 8x plus 1 over x squared plus 1 is equals to 1.577.
Not only that, but to make the surgery of Dr. Yun possible, we also solved the formula of anesthesia needed to put his patient to sleep within the 5-hour time frame.
Therefore, Dr. Yun will need a dosage of 1.577 ml of anesthesia for his patient to stay asleep in the whole 5-hour surgery. Here is the graph, and as what you can see, the limit as x approaches to 5 is indeed equal to 1.577.
Hope you learned something from our topic. That is all for today. Thank you and see you in our next video.
We are the Algebros, at your service. We are here to make you more interested in the field of basic calculus. I am Evian Acosta, the head of our team.
I am Slara Garzon, the assistant head.
I am Shifter Marie Monteza, the researcher.
And I am Francesca Caballero, the editor.